Our objective in this video will be to go over 3 commands and make sure we know how to use them. So let's first load up library reg class, and with this loaded up, we need to load in some data. Of course, you guys know my favorite is using data from survey 10. Nice and easy, I like the numbers in it. So we have survey 10 data and it is now loaded in. With survey 10 data now loaded in, let's start by doing a linear model with height and weight. We are just creating a linear model right here and storing it as M, and we are going to predict height using weight, and these have capitals to start. We have to make sure to tell it what data it's in. It is in our survey 10 data set. So we have y tilde x and data equals, and we've created our linear model. This first command we're going to take a look at is going to investigate whether or not weight should have a polynomial term. And what that means is when we go from a first order term to a second order term, we get a parabola, we get a bend in it. If we go to a third order term, it can bend again. Every time you go from second to third to fourth to fifth, you add one more bend possible in the model. And you guys have seen a straight line before, and you've seen a parabola. Parabola just has the squared term in it. So that's what you're going to see in this output right here. When we do the choose order command, we are actually going to look at, and if you don't see choose order, it's because you don't have library reg class on, so you should see choose order. We want to look at this here and see what model is the best and which one we should use and why. So let's talk about that. Here we are. Well, our output is too tiny, but let's zoom in. This is excellent. And actually, I'm going to try and make this bigger so we can make it nice and neat. It didn't show all the colors of my line, which I love to see. And so we're making this nice and bigger, and hopefully this time when it prints out nice and neat for us. There we go. It's just because that box is so large. And we can try again, but let's see here. Better and better. You'll notice the straight line is one of the most pronounced lines. And then also we have the red and the green line. Those two are kind of close together. Then you notice these purple, blue, and light blue lines. Now this is the 6th, 5th, and 4th. 3rd and 2nd are the green and red, and the black is the first order. What does that mean? Well, a straight line is just to the first power. If you notice, the second is the red line, which just has a parabolic bend to it. It's hard to tell, but the third order also has another bend, and you can tell these 4th, 5th, and 6th have more bends in them. The purple being the most bendy, as you see it bend even more throughout here than the other ones. And what does this mean? It means that it's better able to describe the points, so thus r squared would be higher. But here's the issue. R squared will always go higher when you add in more terms or more polynomials. It's not fair to look at r squared for these. We should investigate r squared adjusted. And you'll notice, as I said, the 4th, 5th, and 6th are very similar. The 2nd and 3rd are similar, and the 1st is by itself. Because the ones with the best r squared adjusteds would be the highest ones right here. This is the best r squared adjusted. And frankly, we should use this one. Probably. I say probably because it's the best r squared adjusted, but it's also the most complex. That's a lot of bends throughout the model, and that's a lot of terms in the model. Very, very, very complex. So which one should we use? The answer is take your best r squared adjusted and subtract 0.005. That has nothing to do with significance, which is 0.05. It just is what we subtract. And what we'll say is we will use an r squared adjusted that is just as big or bigger than this. And you notice 4301, 4308 is bigger, but we can't go down to this one. So what we would choose to do here is use the 4th order polynomial term. Why? Because the 6th was the best, but we're willing to go down to the 4th. And if you notice, the 4th is just like it. It looks very similar. It does just as good. Interestingly enough, when we get to AIC, you'll see that this also has the best AIC. Lower AIC is better. So funny enough, it has the best AIC, and also it meets our term of we want an r squared adjusted that is the best, but we're willing to go down 0.005 off the best. So with this in mind right here, this would be the one we would pick, and the answer for this would be 4. We would choose the 4th order polynomial term. Let's also get another one here. So for the next one right here, we're going to add an interaction term in this model. And an interaction term we will cover more in depth, But we could look at an interaction between weight and GPA. And I'm not going to interpret this right now, but I'm just creating an interaction term right there by putting them like that. Now, listen carefully, because this is just the interaction term. If you notice in my model, and let's increase the output right here. If you notice in my output, I now have weight colon GPA. That is the interaction term. But especially for us, this is very important. We want to include the lower order terms. We want weight, GPA, and both their interaction to be in there. So when you do the multiply, you will see in your output down here, let's show the output, you have the weight term, the GPA term, and the interaction between the two. As mentioned, the colon is the interaction. If you put this in alone, you will only get the interaction. If you multiply them, you will get the interaction term and also the lower order terms. So if something were to say make a model of 1 and 2 and the interaction between 1 and 2, you definitely want to use the star because you would get the first and second variable and the interaction between the first and the second variable. Lots of good stuff going on down here in our output. We have our estimates of the coefficients for all the variables in the model. We have the standard error, which is our uncertainty. We have the t-value, which is our standardized way of talking about how far away the estimate is from 0. And also we have the p-value telling us if those estimates are statistically significant. So lots of good output right here. And this is how to add in an interaction term and also include the lower order terms. You notice in my model down below, I have in weight and GPA, and then also I have the interaction between weight and GPA. Important that you add the star if you want to get the lower order terms, which would be something like include the first and second variable and the interaction between the first and second variable. Hint, hint, hint. But last but not least, let's go ahead and put in this model here with two variables in it. It has weight and GPA, and let's switch back. We're changing the model now, so it just has two variables. It no longer has an interaction term, just has two variables. And what I'm going to do is I'm going to do an extrapolation check. So to do the extrapolation check, we can run our extrapolation command on here with extrapolation check. But what we need to put into extrapolation check is our model and then give it a vector of new data. Well, I already have my model, which is M, but I don't have my toPredict data set, which is just what I'm using to make predictions or check extrapolations. So the toPredict data set will be my new data, and the new data will equal toPredict, but I need to make it. It does not exist. You'll notice over here, there is no toPredict data set. So let's make toPredict, and you can call it to.predict, or you can just call it TP, whatever you like. We're going to save into it, and that's just the arrow right there. And we need to make a data frame. What is a data frame? A data frame is everything you see over here, which is now being blocked. Survey 10 is a data frame. Data frames look like this. They just have information in them. So we're making that right here. Well, think about this. I need to feed it my X variables. So I need to make a data frame now that has in it weight, and my data frame would also have in it GPA. But this is not going to be enough because I need to put in values. Well, we can just do it for one value, and let's do that for the moment. We'll put in a weight of 160 and a GPA of 3.5. And we should get right here, there it is. There's our toPredict data set. And you'll notice there's the person. This first person had a weight of 160 and a GPA of 3.5. So we've created this data frame right here, and that's the whole point of it. If you'll notice, these are my X variables. Weight and GPA are my X variables, which are going to be fed into this model M, which will predict height. Now, I'm not predicting height. I'm seeing how extreme these variables are. I'm seeing if this combination is an extreme combination and what percentile it would be in. So let's go ahead and take a look at the percentile these points would be in. And we're looking at a multivariate combination to talk about is the combination of points in outlier. And here we are. My points are in the 17th percentile, but let's make a change or two. Let's put the weight to 260. And now my points are in the 96.4th percentile. Well, let's put the GPA at a 4.5. Now my combination of points is in the 98.3 percentile. Do you see that they're becoming more and more and more extreme? If I put this to 290, that's going to make it a more extreme combination, just barely. But still, I would say things in the top 5% or the bottom 5% are extreme. They're in the very low or the very high percentile for our data set. And so we don't really have combinations of points that are this far away from the central x's right here. Because each x has a mean, and we're talking about how far away this combination is in a multivariate sense, which is only bivariate here, from the mean of the x's. And we could check more points at once by doing this, concatenating. The first person weighs 200, the second person weighs 300, the next person weighs 150. The first person's GPA is 4.0, and then we have 2.0, and then we have 4.5. Now when I make this, you'll notice, just as I said, 200 with a 4.0, 300 with a 2.0, 150 with a 4.5. Everything nice and neat there for us. Now when I do the extrapolation check, I will get in 3 different ones. It turned out pretty interesting. One of the points is pretty much what I would say in extrapolation. It's pretty far out there, and I don't think our model is going to make good predictions for it. And that's why we do this, to see if we really should be making predictions for these points. And that's why we use the toPredict on it. Should we really do a prediction with this point? Not so certain. And that will do it. That has the toPredict function with the extrapolation check. We've done the polynomial order, and also we have investigated an interaction term. Good luck, and email me if you have questions.